Hello, I'm Richard with EV4U. In this episode, we'll introduce solar panels, wind turbines, hydropower, fuel-powered generators and inverters, DC circuits. So let's get started. Currently, there are 5 main types of solar panels. Monocrystalline panels, which have a high power output and have long lifespans, and they are 18 to 24% efficient. Polycrystalline panels are less expensive, but only about 14 to 18% efficient. PERC panels typically perform better than traditional panels in both low light conditions and high temperatures, but at a higher cost. They're about 23% efficient. Thin film panels are thin, light, and flexible with efficiencies around 7 all the way up to 18% efficient. They are the least expensive, but they have the shortest lifespans. Bifacial panels are a little more expensive, but can have up to 30% efficiency depending on the setup. Monocrystalline solar panels are currently the best option in terms of efficiency and cost, with bifacial panels becoming more and more popular. We'll take a more in-depth look at solar panels later in this video series. Wind generators are a great add-on to your off-grid power system. They work best in areas where the wind is fairly constant. However, wind turbines produce noise and can alter the visual aesthetics of your property. There are 2 basic types of wind turbines: horizontal axis turbines and vertical axis turbines. Your location will dictate which is the better choice. In general, wind turbines begin to produce power at wind speeds of about 7 miles per hour. A turbine will achieve its nominal or rated power at approximately 26 to 30 miles per hour on average, depending on the type and the unit used. Seems like they're coming out with new designs all the time. The advantage of wind versus solar is that wind can blow day and night. A disadvantage is that they require more maintenance than a solar system. And we'll take a more in-depth look at wind turbines later in this video series. Most hydropower systems used in small off-grid systems are referred to as micro-hydropower systems. Hydropower systems convert the mechanical energy of flowing water into electrical energy. There are several designs available. The most common types are the Francis, Kaplan, and Pelton turbines. Francis turbines are the most commonly used type and have a radial flow design, which is more than 95% efficient. A good hydropower system requires year-round flowing water with enough volume and elevation drop to meet your needs. The design of a micro-hydro system requires measuring the head, that's the vertical drop, and the flow of the stream in order to calculate the energy potential. The beauty of this method of off-grid power is that it can operate 24 hours a day, unlike wind and solar. However, freezing conditions can be a limiting factor. We'll take a more in-depth look at hydropower turbines later in this video series also. A fuel-powered generator or inverter is recommended as a backup system only. This is because they require fuel to operate. They have maintenance requirements as well as location considerations due to safety issues. They also produce noise and oxide gas. Another consideration is, say, fuel storage. What's the difference between a fuel-powered generator and a fuel-powered inverter? Well, a fuel-powered generator produces electricity directly from a combustion engine, typically running at a fixed speed, powering an alternator. While a fuel-powered inverter uses an internal combustion engine to generate power using an alternator, but it converts alternating current, AC, from the alternator into direct current, DC, and then back into AC. This process produces a more reliable electrical current than the traditional generator. This is because the inverter's electronic circuitry filters out distortion, voltage fluctuations, and electrical noise. The result is a consistent electrical current that's ideal for powering sensitive electronic devices. Fuel-powered inverters also offer better fuel efficiency, reduced emissions, and run quieter because they adjust their speed based on the electrical load. However, a generator is better for high power needs like running heavy appliances. We will take a more in-depth look at fuel-powered generators and inverters later in this video series. To help us prepare for reading and using schematic diagrams later on, let's look at some of the basic symbols that we will be using. This is the symbol for a battery. This represents a ground connection. Most automobiles use a 12-volt negative chassis ground setup. This is a symbol for a fuse. This is the symbol for a switch that is open. This is the symbol for a switch that is closed. This is the symbol for a light bulb. And this is a symbol for a meter. And you can see the V inside there. That means it's a voltmeter. If there's an A, it would be an amp meter. A W for a watt meter, that type of thing. A direct current DC circuit is a circuit in which the power is from a DC source, like a battery. The current in a DC circuit only flows in one direction, from negative to positive. A DC circuit is an electrical circuit that is a closed loop of electrical components that allows the electric current to flow. An example of a simple circuit would be one in which current travels from the negative terminal of a battery through a wire to a load, such as a light bulb, back through another wire to the positive terminal of the battery. Here's an example of a battery providing current to a light. You'll notice that there's also a fuse and switch in the circuit. This is the most basic circuit for practical use. In the circuit, the light would be off because the switch is open. In this example, the light would be on because the switch is closed. There are 5 types of electrical circuits: an open circuit, a closed circuit, a short circuit, a series circuit, a parallel circuit. Again, this is an example of an open circuit. Current cannot flow in this circuit because the switch is open, breaking the circuit. Thus, the light will not be lit. Here is an example of a closed circuit. The light will be lit because we have a complete uninterrupted path for current flow. These 2 circuits are examples of series circuits. A series circuit is where all circuit elements are arranged in a single path. In a series circuit, the current through all the elements is the same. This is an example of a short circuit. Notice the short between the fuse and the negative battery terminal. This short would cause the fuse to blow, which would open the circuit and protect the battery. Due to the open circuit blown fuse, the light will not be lit. If we didn't have the fuse, then something would have to give. You'd either damage the battery or the wire would melt, possibly cause an issue. Always remember that electricity follows the path of least resistance. In the short circuit, the short is the path of least resistance. Here's an example of a parallel circuit. In a parallel circuit, the electrical path branches so that the current divides and only part of it flows through any branch. The voltage or potential difference across each branch of the parallel circuit is the same, but the currents may vary. Quick summary: DC circuits have a positive and negative polarity. Series circuits, the current is the same through the entire circuit. Parallel circuits, the branch circuits equal the total of the circuit current. So the total current through the battery would be the sum of your individual branch circuits. Now let's look at batteries wired in series. In this example, there are 3 12-volt 100 amp hour batteries in series, and that's going to give us a 36-volt 100 amp hour battery pack. In a series circuit, the positive of the first battery is connected to the negative of the next battery, and so on, as you can see in the diagram. If we have 3 12-volt 100 amp hour batteries wired in series, the potential is 36 volts. Current available is 100 amp hours. The voltage is multiplied by the number of batteries, but because they're in series, the current capacity remains the same. The same current flows through the entire circuit. Another option for wiring our batteries is a parallel circuit. That means that we connect the positive from one battery to the positive of the next battery, the negative of the first one to the negative of the second one, and so forth. If we have the same 3 batteries, so we have 3 12-volt 100 amp hour batteries, But wired in parallel, the potential is 12 volts and the current capacity is 300 amp hours. Capacity is multiplied by the number of batteries, but because they are in parallel, the voltage remains the same. So just looking at the diagram, you can see 12 volts, but you're going to have the additional capacity because of the way those are wired in parallel. Note that storage capacity, watt hours of the battery pack, remains the same, whether the batteries are wired in series or parallel. Remember from our last video that capacity in watt hours is calculated by multiplying the voltage times the amp hour rating. So in the example, we have 12 volts times 300 amp hours, 3,600 watt hours. That's in series. In parallel, that was in parallel. In series, we have 36 volts at 100 amp hours. So again, doing the math, 36 volts times 100 amp hours equals 3,600 watt hours. So it doesn't matter whether they're in series or parallel, capacity of that battery pack would be the same. But the current available, the voltage available, will vary based on whether it's series or parallel. So to increase the voltage, you wire the batteries in series. To increase the current available, you wire the batteries in parallel. This series circuit consists of a 12 volt battery, a switch, two 24 watt light bulbs, and an amp meter. If we close the switch, how many amps would the amp meter read? We're going to refer back to Joule's law that we talked about in the previous video. Remember the formula for power? Power is equal to volts times amps, or E times I. Also, do you remember how to calculate for current? Well, the formula is current is equal to power divided by volts. So the power in this example is 48 watts. We have the two 24 watt bulbs in series, so they add, so that's 48 watts. 48 watts divided by 12 volts is 4 amps. If we open the switch, the amp meter will read 0, because with the switch open, no current will flow in the circuit. So why does it matter how much current's flowing in the circuit? Well, in order to determine the correct wire size and the correct size of fuse, we need to know the current flow in the circuit. If you use wire that's too large, you're wasting your money. A wire that's too small will get hot and can melt and possibly start a fire. This circuit is a parallel circuit. Note that there are 3 parallel branch circuits. In the branch to the far right are 2 light bulbs in series. We are asked several questions within this example. Let's start closest to the battery and move to the right. In the first branch, there is a 36 watt bulb, and we're asked for the amps in that branch circuit. It's a similar equation to one that we just did in a series circuit. We need to solve for the current, which is current is equal to power divided by volts. Well, if the power is 36 watts and the voltage is 12 volts, then 36 watts divided by 12 volts equals 3 amps. The next branch is missing the wattage of the light bulb, but the current is given. The formula again for power is equal to volts times amps. 12 volts times 3 amps will give us 36 watts. Next, we're asked what the current is in the far right parallel branch. Note that in a parallel branch, the total circuit current is the sum of all the branch circuits. We can see that the total circuit current, notice the amp gauge at the bottom left is showing 10 amps. This means that this branch circuit, far right, is going to be 4 amps, as the other 2 branches were 3 amps each. So that adds up to 6. So 10 minus 6 equals 4. So next we need to figure out what the wattage is of the light bulb at the bottom of our schematic. Well, again, we're going to solve for power. Power is volts times amps. We just calculated there's 4 amps in that branch, and we have 12 volts across that branch, so the answer is 48 watts. However, there's a 24 watt bulb in the branch as well, so we subtract that from our total branch power of 48, and that leaves us with 24 watts for the bulb at the lower right. Let's look at a different circuit. In this circuit, let's answer the following 3 questions. What type of circuit? What's the total voltage? And what's the total current capacity in amp hours? Well, it's a series circuit. So we know that the voltage is going to multiply. So 12 times 2 is 24 volts. And I just answered it. It's a series circuit, so that's the answer to the first question. 24 volts is the answer to the second question. And the third question is the total current capacity in amp hours. Well, it's a series circuit, so the capacity will be the same as the individual, so it's 130 amp hours. Now let's look at this one. This is, again, the same 3 questions. What type of circuit, total voltage, and total current capacity in amp hours. You can see that, positives are connected together, negatives are connected together. This is a parallel circuit. And what's the voltage? Well, the voltage stays the same. It's going to be 6 volts. The total current capacity is going to multiply. So it's going to be 490 amp hours will be the total capacity. So we've got 6 volts at 490 amp hours. To summarize, in a series circuit, the total power is the sum of all power used. Current flow is the same throughout the circuit. An open circuit results in no current flow. In a parallel circuit, the total circuit current equals the sum of the branch currents. The voltage is the same across all of the branches. Knowing the current requirements of a circuit allows us to use the correct size of wire and fuse, and wire and fuse charts are available on the internet.